Hi everyone, welcome to this course on Python for machine learning and data science. My name is Marco and I'll be your instructor for this course. Here is an agenda of what we're going to learn today. So we're going to look at mainly three areas. So mathematical calculation, data frame manipulation, and visualization. We're going to learn these three topics with the aid of three very important packages in the Python and data science community. So we're going to look at NumPy, which is a package used for numerical and algebra calculation. We're going to look at Pandas, which is a package used for manipulation of data frame and tables. And then we're going to learn how to use Matplotlib and Seaborn. These are two of the most popular Python package for visualization purposes. So what we're going to do here today is understand how these packages work with the examples in code and with the aid of a Jupyter Notebook. So without further ado, we can start and look at NumPy. So NumPy is a Python package that stands for Numerical Python. Is a package designed to enhance the capabilities of standard native Python in order to be able to do mathematical and linear algebra operation. Is one of the most important core library for scientific computing. It contains a lot of powerful n-dimensional array object and operation, and also it provides tools for integrating C and C++. Here I have prepared a notebook, which we're going to share and go together to see the most important characteristic of NumPy and how to use it. So first, how we get NumPy working. The first thing we should do is installing NumPy. Now, NumPy can be installed in several ways. One of the most common one is to use pip install. So pip is the package manager for Python. So we can just type, as you see here, pip install NumPy, and we can get the package installed in our environment. After that, we need to tell the compiler that we want to use it. So we can import the package, writing import NumPy. And then, as we do here, we give an alias. So import NumPy as NP. This is called an alias, and it will allow us to basically speed up the writing of our commands. So rather than typing the full NumPy, we can just type NP. Is something that is optional. You don't have to do it, but it's nice to do it because, as I said, it speeds up the calculation. So this is the very first command that we're going to run in our session, import NumPy as NP. And when I run it, it runs without error and basically is loading up the functions available in the NumPy package. It's basically telling the compiler, I want to use all the functions in NumPy, please make them available to this session. And this is exactly what this command does. So one of the most important object available through NumPy is the NumPy array. Now, the concept of array basically resembles the concept of a vector in a standard mathematical terms if we're talking about a one-dimensional array, or a matrix if we're talking about a two-dimensional array, or if we go three-dimensional and more, resembles the mathematical concepts of tensors. Now, in Python, there is an object already which basically allow us to store more than one object at a time, which is the list. However, NumPy arrays are more convenient to use rather than Python list because are more memory efficient. Therefore they can be used in operations which are faster, and they're more convenient because NumPy, all the NumPy functions that we're going to use are designed to work with NumPy arrays. So it's nice to have everything working in the same ecosystems and everything is compatible to each other. So we don't have to worry about compatibility problems. Whereas sometimes if we use Python lists, we may run into compatibility problems for some operation that we're going to do. So as I said, we're going to start using NumPy array. And the first thing to do is actually create some arrays. So what we can do is create, as I said, some arrays from standard Python list. So what we do here is create two variables. One is called person height, and the other one is called person weight. So the first person height, which is the first variable, is basically a list of 5 numbers, standard Python list of 5 numbers. So we have 5.2, 5.4, 4.4, 4.5, 5.6, and 6. Similarly, we create another variable which is called person weight, which again, as you can recognize from the square brackets, is a standard Python list. So again, 6 numbers: 81, 55, 65, 70, 45, and 44. So at this stage, these are two Python lists, one called person height and one called person weight, which contains some numbers. Now, we said we want to work with NumPy arrays, and therefore we need to convert these lists into an array. And very easy to do that, and we can do this with the function array. So person height is basically np. Remember, we need to call the package the function's array, and then as the argument of the function is our list. So np.array person height, and same thing, np.array person weight. So as you can see, they are the same name, so we kind of overwriting those lists, and so those lists do not exist anymore in the form of standard Python list. They exist, however, in the form of NumPy arrays. And one thing to notice is that when we print to the screen person height, we see that is in fact an array, and it tells us the numbers or the component or the element. It tells us the elements of the arrays. And similarly, when we print person weight, we have the same view. So it tells us that is an array, and we have the elements of the array printed to the screen. If you want to make sure, we can print the type. So the type is basically saying, okay, what is this object? And is a NumPy n-dimensional array. So this object is basically an instance of the class NumPy n-dimensional array. Now, we have only one dimension in this case, because we don't have a matrix or anything more complicated. However, it still belongs to the class of NumPy non-dimension. So basically, we learned how to create NumPy arrays. And the way we do that is starting from standard Python lists, we can convert them into an array. Super easy and super convenient way to create NumPy arrays from Python lists. Again, the reason why we want them to convert them into NumPy arrays is because they are faster. They are designed to be used and be the argument of mathematical functions. And as we can see, we're going to use NumPy arrays to make several kind of calculations. What we're going to do here with arrays is understand and learn how to index or array. Sometimes this is called slicing, is a different word for basically the same concept. So slicing or indexing basically means within an array, on n-dimensional array as we see today, we're gonna extract only one specific element. So we start by creating an array, as we know now how to do it. So we call np.array, and as the element of the parameter or the argument of the function np.array, we give our array. In this case, is a numerical array of 6 elements. and then we can print it to the screen. And here we have our array. We said we want to index or slice an array. So basically we want to access the individual component or element of this array. And we can do this with square brackets and give an index. One thing to remember is that Python starts to count from 0. So the first element is element number 0 and not element number 1. I understand it may be confusing, but Python starts to count from 0. So basically, when we give the instruction of print my array of position 0, we're basically asking for this number here. So element 11 in this context, in this array. Whereas we ask for my array position 2, we ask for the third element, which is 33. 0, 1, 2. And in fact, we have here 11 and 33. So basically, this is a way of slicing or indexing an array. And the way we do this is basically with square brackets and give the position, remembering the start from 0. There are several ways why we want to access individual element within an array or within a vector. And that's the way we're going to see more about this later, but this is the way to do it. As we said, Python does not, and more specifically, NumPy does not only support one-dimensional array, but also two-dimensional array, which you guys may be familiar in mathematical terms as matrices. So we can basically see here, I'm going to arrange everything to make it clear. So basically what we're giving here is a two-dimensional array. And how we do this? So as always, we call this variable myArray. And as always, we use the np.array function. And the parameter or the argument of this function is basically a list of lists. It's basically an array of arrays or a two-dimensional array. In fact, we have the initial square brackets open, then the first row of our matrix, comma, second row of our matrix, which is a list on its own, comma, third row of our matrix, and then we have the closing square brackets which enclose the full matrix, and then we close the bracket of the array function, and then we can print it to the screen. What it's telling us is basically an array, and these are the elements. As always, we can retrieve, index the element of the array with square brackets. So in this case, remember, is a two-dimensional array, so we need to give two dimension. In this case, we give element 2, position 2, and element at position 1. Remember, first are the rows, and second is the columns. So basically, we're asking position 2 for the rows. So position 0, position 1, position 2, and then the position 1 for the column. So this will be position 0, and this will be position 1. And in fact, we have here 821 printed, because we are only accessing this element from this all big array. So second, which is in really third element of the row, and position 1, which correspond to the second column, 821, as we can see here. We don't have to use this notation with first element, comma, second. We can also slice first on the rows and then on the column. So if we don't specify anything, the first bracket refers to the row, and we access the full row. And then on the full row, access element number 1. This is a little bit more verbose of a way, that there's more code to write, whereas this is a more compact notation. However, this is handful if we need to access the full row, we can just say myArray2. So if we just need the third row, we just give myArray2, and that's the full row. And in fact, this is exactly what we do here. So we pick the second row from the array. So we say myArray second row, which in reality is the third, and this is printed here. So as you can see, there is no comma, and that means give me the full row. Again, this is not the only way of doing this. We could have done with two elements. So n is what we see here. This is more explicit of saying, and we have this column here. So this is another way of slicing an array, which I'm going to explain now. So basically, we are using the two dimension notation, and in fact, you can see there is a comma. However, if we do not specify the first element and we just say column, that means give me the entire element belonging to that specific dimension. And basically we're saying, give me the full first dimension, which we know are the rows, and give me the second column, so which in reality is the third. And as you can see, these correspond to 321, 321, 622, 912. Because again, we are saying, give me all the rows, and that's why there is a column belonging to column 2. So column 0, column 1, and column 2. Which rows? All of them. And in fact, we have them all. 321, 62, 912. 321, 622, 912. For printing purposes, is displayed horizontally rather than vertically. But this is exactly what we are doing. And that's how we index the element in the arrays. Well, another way of using this notation with the two, like basically with the column, is to get intervals or sub-intervals of an array. And you have an example here. So we have the first array here, 101, 121, 112, 123, and 114. So I can say create new array, which is the old one. Which one? From position 1 to position 4 minus 1. And I'm going to be explicit what this means in a second. So basically, when we say 1 column 4, basically we're saying 1, 2, and 3. Remember, we get all the elements up to the number that we specify here minus 1. So in this case will be position 1. We know we start counting from 0. So position 0, position 1 means 121. And in fact, we have it here. Position 2, 112, and we have it here. Position 3, 123 is here. Why do not have position 4? Because it counts up to position specified here minus 1. So in this case, when we say 1 column 4, we basically means 1, 2, 3. So 0, 1, 2, 3. These three elements, and in fact, we have them here. This notation with the column is basically very, very similar to this one. And in fact, it's exactly the same, because when we do not specify a starting or an ending point, like here, we don't have anything on other side of the column. Basically, we are saying from the very beginning, from 0 to the very last element, which in this case would have been element 3, so 0, 1, 2. But as we know, it goes up to the last element specified minus 1, so it would have been 3. If we don't specifying anything, is assumed to be from the very beginning to the very end. And that's why we is basically the same notation, but here is written implicitly without specifying start and end, and here is written explicitly specifying the first position and the last position. And in fact, as you can see here, the first position is not specified, and that means from the very beginning. And in fact, it starts from 101, as we can see here. The last position it is specified is 3, but remember, it goes to 3 minus 1. So it's position 0, position 1, and position 2. And in fact, we see these 3 elements here. Similarly, when we do not specify the last element, it basically means to the very end, from position 2 to the very end. So position 0, position 1, position 2 to the very end. So it will be 112, 123, 114. 112, 123, 114. Exactly as we see here. Or this is a little bit redundant in this case because the array is only one position, but it was very useful when the array was two-dimensional, as we saw before. If we do not specifying anything, means from the very beginning to the very end. In this case, there is no need to do that because the array is only one dimension. But when it's multiple dimensional, it'd be very useful if we want to extract maybe the entire row, but just one row, or the entire column, but just that one column, as we did before. And here, in fact, we have an example. So here again, we have a two-dimensional array, which is basically a matrix in more mathematical terms. Is got this particular array or matrix has 4 rows and 5 columns. So the index of the rows will go from 0 to 3, and the index of the columns will go from 0 to 4. Having these numbers in mind help us to slice or index the elements we need. And in fact, we do here. So here we are saying, give me the array on the row from 1 to the very end. So on the rows, it means from row 1, which is this one, to the very end. So including this one. And from the columns, basically means from column 2, so column 0, column 1, column 2, so this column here, to 2, 4. So 2, 0, 1, 2, 2, 3, and 4. But it's minus 1, so we stop here. So basically, 2 column 4 basically means 2 and 3. And in fact, we see this thing. I'm going to highlight it here. This is what we want. We are slicing this particular submatrix. One more time, from row 1 to the very end. So row 0, row 1 to the very end, and column 2 and 3. Remember, it's always minus 1. So 2, 3. So 2 and 3. And that's what we have here. This, again, is a new array of dimension 3 rows and 2 columns. Operations that can be done with arrays. We create an array. My array 1 is in the usual fashion. So mp.array, and then we give a list, which is an array here with 120, 230, 310, 410, and 150. So 5 elements. And then we create another array. Here we are seeing another way of creating an array, which is with this function arange. So arange is a function that takes an index and based on this index creates an array. I can show you. Basically creates an array of how many elements specified here up to minus 1, starting from 0. So if I do my array 2, we see 0, 1, 2, 3, 4. So 5 elements as specified here, but counting from 0 to this number minus 1. And in fact, we have it here. One important suggestion here is that every time you use a package in Py, and this is always, and is always going to be valid, every time you use a package and you see a functions that you don't know, always look at the official website, because it tells you a lot about how to use that particular package. So the first recommendation is always look into the NumPy documentation. This is an example I'm giving you. So this is the official NumPy website. You can look into the documentation, and here is going to tell you everything about the package, how to use the package, examples, everything you need to know. So, for example, beginner's guide, the user guide, the API reference, or a contributor guide. So now we can look at the API references. The API references is very useful because it tells you how to use the function. We can look for the arrange functions that we just use, and in fact is going to tell us NumPy arrange, so return every spaced values within a given interval. As you can see, it's got several arguments that this function takes. The important one are start, stop, and step, whereas start and step we don't have to specify. There's, if we want, we can specify. If we do not, they have default value. So start is default value to 0. And in fact, what we see here is in fact this value start from 0 because we didn't specify a starting position. Stop, we did, is 5, but always remember is 5 minus 1. So it's going to be 4. And then the step, which is this one, it's not specified. It's not specified and is assumed to be equal to 1. And in fact, it goes 1 by 1, 0, 1, 2, 3, 4. So it's a faster way of specifying an array. We could just as easily could have done this instruction. It would have been exactly the same thing, but by using the arrange function is a little bit more convenient, is faster, and is less code to write. With that being said, now we have two array 1 and array 2, and we may want to add them together. So if we add them together, obviously, this is a very easy operation. We're going to have each element add 1 by 1. And that's what we have. Remember, array 2 is 0 to 4. So 120 to 0 plus 0 is 120. And in fact, we have it here. 230 plus 1 is 231. And we have it here. 310 plus 2 is 312, and so on and so forth. And in fact, with the plus sign, NumPy is intelligent enough to add each element element-wise in the vector. We need to be careful because sometimes if the two arrays are not compatible, we're gonna have an error. So we can create another array with only 4 elements, not 5, 4 in this case, 1, 2, 3, 5, and we can try to add them. If we do this, we're gonna have an error. It's important, when you have an error, it's important to understand the error in order to understand what we did wrong and fix it. So in fact, it says the operands basically means the two arrays cannot be broadcasted together because they have different shape. One is length 5 and the other one is length 4. And since we saw that the addition with arrays add elements in the arrays 1 by 1, basically NumPy is telling you, one, I have 5 elements, the other one has 4 elements. I don't know how to do it, so I cannot do it. These two arrays cannot be broadcasted together, and that's why it's raising an error. When you see this error in your calculation, basically you understand that you have some issues with the dimension of the arrays. The other operation work exactly the same. So if we do, for example, my array multiplied by 4, it's going to multiply each element, in this case, by 4. So my array 1 was, if you remember, we created here 120, 230, 310, 41, and 150. And we multiplied each element by 4, as specified here, star 4, and we have these values, which are the initial array multiplied by 4. We can also get the square with 2 stars. So remember, in order to get the power of a number, I do not use the caret operator, but I use star and star. This is something to keep in mind because it may lead to some error. So it's a double star to raise to a power. And in this case, I get the square of each element in the array. So what do I expect when I give this function? I expect an array the same dimension of the initial one with each element squared. And in fact, this is exactly what I have. So my array 1 was 5 elements, and these are the 5 elements, but they are all squared. NumPy can also be used to compare, like these sometimes are called logical expression. So I create an array 34, 45, 67, 45, 23, 5 elements in the array. And then I create a new array, which is basically the answer to this question I'm asking. Is the element of my array, are the element of my array greater or equal than 40? And then I have these values. So false, because 34 is obviously less than 40. Then these 3 elements are obviously greater than 40. And in fact, I have 3 true. And at the end, I have 23, and therefore is false. This is another array exactly as we saw before, with one difference. So the arrays we saw up until now are all numerical array. This is called a logical or Boolean array, which basically contains false and true, which are logical statement or Boolean statement, and is basically telling us if something respect the condition that we imposed before. False, true, true, false. Is an array exactly as the one before. The only difference is the data type of the element it contains. They are not numbers. They are logical operators, logical statements, Boolean variables, but they are exactly the same. The advantage of having an array in this format is that it can be used to index an array. So when we're gonna see in a second how this is done, but the advantage is that when we say in an indexing fashion false, we do not want that element. Whereas when we say true in an indexing fashion, we do want that element. So if I use this array as the index of a previous array, is basically saying, okay, give me these 3 positions. So position 1, remember 0, 1, 2, 3, 4. So position 1, 2, and 3. And in fact, if I do my array and new array, and remember new array is this array of true and false, I'm basically asking for this element here. As you can see, false, true, 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 false. So false, 3 trues, and then a false. And in fact, I have these 3 elements, 45, 67, 45 here. I don't have to create an array and give it to the argument of the indexing. I can just write here directly the condition to make it faster. So basically, if I want to slice an array based on a condition, I just specify the condition in the bracket. So I only retain these elements that satisfy this condition within the brackets. Because false means do not take the element, whereas true means do take the element instead. We're going to look now at arithmetic functions in NumPy. So there are several arithmetic functions or mathematical functions in NumPy that can be applied to arrays of any dimension. Since we are using NumPy functions, they're perfectly compatible with NumPy array. And we're going to see some example here. So as always, we create an array. So in this case, we have a NumPy array of 5 elements, 5, 7, 8, 2, 4. And we have it here. So the first thing we can do is get the sum of the element of the array. using myArray.sum. Now, this is something a little bit different than what we saw before, because before we saw functions from the NumPy library. And in fact, if you recall, it was always NumPy.sum specific function. In this case, we have myArray.sum. This is something a little bit different. This basically we're saying use the method sum from this class, from the array class. And in fact, we get the sum. Something equivalent would have been numpy.sum and then myArray. So as you can see, the result is exactly the same, 26 and 26. Here we are taking the numpy sum functions and apply to the myArray. Here we are calling the sum method from myArray class. Now, behind the scenes, they do exactly the same thing, as in fact the result is the same. However, there are two different ways of doing the same operations. And you will learn, as you will learn, there are several ways. Usually, there are several ways of doing the same operations. And our job is basically to find, when it's possible, the most efficient way of doing it. Or sometimes, like in this example, we can just pick and choose the one we prefer. There is other functions available. For example, we can find the minimum value. Similarly, we could have done np.min and then myArray. We could have done the max value if we wanted to do. In this case, we're doing power. So we do numpy.power, myArray, and then the exponent. And that basically we take in the cube of each element in the myArray array. Similarly, as we saw before, we could have done myArray ** 3, and would have gotten the exact same results. As I said, NumPy has a lot of functions, and we can see here all the mathematical functions that NumPy has in the guide. So, for example, here we have mathematical functions, and we have trigonometric functions, hyperbolic functions, rounding, sums, as we saw here, products, differences. There are a lot of mathematical functions that we can use. My need to use any of these functions, they are all here, and we can choose what we need. As I said before, since that these functions in the NumPy library, they can be applied without any problems to NumPy arrays, as we saw here, without any errors, without anything to be concerned about. We just get the result straight. Another thing we're going to look today is array concatenation. So concatenation array basically means putting some arrays together and create a big array. So for example, here we have this array X, which is array of these three elements, 11, 22, and 13. And we also have this array Y, which is an array of these three elements, 23, 22, and 12. We concatenate them. So basically, we put them together. And how we do that? We have this function, np.concatenate, and we create a list with these square brackets of the arrays we want to concatenate. And as you can see, in fact, the result is the first array and then the second array here. We can also concatenate, obviously, more than two arrays at once. As a matter of fact, concatenate as many as we want. We just add this array Z, and in fact, the result is exactly the same as this one, plus these additional two elements from array Z, 23 and 45 here. We can also concatenate two-dimensional arrays, basically matrices, and we can take a look how to do it. Now, the difference with matrices is that we need to specify the dimension. Since there are multiple dimensions, we can specify along which dimension we want to concatenate, whereas with one-dimensional arrays, this is pretty obvious that we want to add them at the end. We're going to see an example now. As always, we create an array, in this case a two-dimensional array. So an array of arrays, 1, 2, 3, 4, 5, 6. We have them here. So we can concatenate along the first axis. So basically stacking one on top of each other. And in fact, we have here 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. We don't have to specify the axis. So x is equal to 0. We don't have to specify because it's assumed to be along this axis by default. If we want to concatenate one on the side of each other, we instead specify along x is equals 1. And in fact, we have it here. 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. The reason why we specify x is 0 and x is 1 and exactly this number, if you remember, when we were slicing arrays, the first coefficient before the comma identifies the rows, and here identifies the columns. So here is position 0 or x is 0, and here is position 1 or x is 1. And that's why when you say x is 0, basically means the rows, and in fact is one on top of each other, and x is 1 is the columns, and in fact is one near the other. And we have it here. If we have multiple dimension, we could also have x is 2, 3, 4, and so on and so forth. We need to be careful when we concatenate the array, because array can only be concatenated if they have the same dimension. So as an example, here we are trying to concatenate array x, vector, one-dimensional array, and this matrix, my array, here, which is this matrix here, a two-dimensional array. Obviously, they're not compatible, and in fact, we have an error. All the input arrays may have the same number of dimension, but the array index 0, which is this one, array x, and we know is a vector, has one dimension. And the array index 1, which is this one, we know is a matrix, has two dimensions. And therefore, they are not compatible. NumPy doesn't know how to add them to each other because of these reasons. So make sure to concatenate array of similar dimensions. As I said before, we need to be able to learn, like understand and read and understand the error messages in order to understand what we need to fix in order to make this work. And now we see exactly why this is not working, and we know how to fix it. An operation which is the inverse of concatenating arrays is splitting of array. So in this case, we split the array into subarrays. So we create an array. In this case, we create an array of 8 elements going from 0 to 7. And in fact, we have it here, 0, 1, 2, 3, 4, 5, 6, 7, with the arrange function. And we want to split the array. So we say numpy.split array x, which is this one. And then we need to specify how many new array you want. In this case, is 2. Now, when it's not specified where to split the array, the compiler, the package, is trying to create 2 arrays of equal dimension from the original one. And in fact, 8 divided by 2 is 4. So we have 4 elements and 4 elements. We can also specify the cut point, so where to split the arrays, as we did here. So we have split the array x at cut point 5 and 7, at the indices 5 and 7. So in fact, we have index 0, 1, 2, 3, 4. At 5, we cut 5, 6, and then at 7, we cut again. And in fact, we have it here. So here we're not specifying how many arrays we want in return. We're just specifying where to cut, basically the split point. And that is what we have here, like this: 0, 1, 2, 3, 4, 5, 6, and then 7 because we specified the indices. One thing to bear in mind is that when we do not specify the indices, but we just tell the compiler how many arrays we want, in this case, for example, 3, exactly as we did 2 before, we need to make sure that the dimension of the array and the number of the subarrays we want are compatible. For example, here we have an array with 8 elements, and we want to split this array and give 3 subarrays. Now, 8 is not divisible by 3, so we cannot have 3 equally sized arrays from an array of size 8. And in fact, we have the error. Array split does not result in equal division because 8 divided by 3, it's not, it doesn't return an integer. If this, for example, would have been an array of 9 elements, we wouldn't have not any problems here, but we would have had a problem here because we couldn't now have 2 same equally sized array of from an array of 9 elements. So we need to make sure that the array's dimension and the number of subarrays we want are compatible, which basically means divisible to each other. There is another function, however, which is called array split that helps us in this situation. In fact, here we do array split of the same array and we do not have any error, even if we say 3 subarrays. The way in which this one works is that it's trying to, do this division, trying to avoid errors as much as it can. And in fact, when we divide an array of 8 elements into 3, we have 0, 1, 2, 3, 4, 5, and then the remainder of the division. This is basically what this thing is doing, is trying to split the array anyway, leaving the remainder at the end. And it's called array split. If, for example, we would have used array split in 2 subarrays of a dimension 4, we would have had 4 and 5. So a dimension 9, we would have 4 and 5. That's what it's trying to do, leaving the remainder at the end. There are other 2 important functions to talk about, which we're going to talk now, which is vsplit and hsplit. Vsplit is a vertical split, and hsplit is horizontal split. When we have arrays of multiple dimension, we can do vertical and horizontal split to split along one of dimension, so either rows wise or column wise. And let's have an example. We have the first function, as we always do, np.arrange. So np.arrange, as we know, is creating a vector, a one-dimensional array of 20 elements, going from 0 to 19. This is something that we did not see before. It's called reshape. So basically, is reshaping or casting this array into a matrix of 4 rows and 5 columns, as we see here, 4 rows and 5 columns. This is another, and I'm going to give you an actual example, is another situation in which we need to be mindful about the dimension, because if they are not compatible, we're going to have an error. In fact, it says, cannot reshape an array of size 20 into shape 4, 4. 4, 4 basically means an array of size 16, but array of size 20 obviously cannot be reshaped in a matrix, is not compatible with a matrix of 4 rows and 4 columns. So this is another situation in which we need to be careful. If, for example, here we do 16, we don't have any issue. So basically, going back to what we were saying, we want to create a matrix in order to try this vsplit and hsplit function. So we create an array of 20 elements, and then we reshape in a matrix 4 by 5. So bsplit basically splits vertically, so basically row wise down the rows, and is basically cutting this halfway. So we want two sized, two equally sized sub arrays, and in fact basically is cutting alongside the middle vertically. Basically is an horizontal cut, but is done row wise, and that's why it's called bsplit. It may be confusing, but this is the reason. So it's counting vertically: 1 row, 2 rows, 3 rows, 4 rows. We want two equally sized arrays, so it will count vertically 4 divided by 2, which is 2. So 1, 2, and then cut here. And in fact, we have the same thing: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 here. And then the other one, this one here: 10, 11, 12, 13, 14, 15, 16, up to 19. Hsplit does exactly the same thing. So we can create an array, in this case 16 elements, which we reshape into a 4x4 matrix, and 16 is perfectly compatible, and in fact we don't have any errors. And then we split. Hsplit splits column wise, so basically says count horizontally how many columns. In this case, the original arrays had 4 columns, and we want two equally sized array. So 4 divided by 2 is 2. So count horizontally 2, 1, 2, and then cut here. And then it's cutting along this line here. And in fact, we have the first one: 0, 1, 4, 5, 8, 9, 12, 13 here. And then the other subarrays here. So hsplit and vsplit, in order to split multi-dimensional arrays vertically or horizontally, basically row-wise or column-wise. So this was the end of this first lesson on NumPy. There's way much more to know and to experiment. My personal advice is to go on the NumPy website, look at the documentation, look at the guide, getting start, and experiment with this library, which again is the core library for mathematical and algebraic calculations in Python. Is very, very powerful. So experiment with NumPy and try different functions, and review obviously the material we did today in order to understand how to use it and to interpret the results or the errors you may have. Pandas is another Python library that contains data structure and data manipulation tools designed for data cleaning and analysis. It is entirely built on the concept of series and data frame, and all the functions and methods in the library are devoted to data manipulation around data frame. Data frame or tables, so basically structured data stored in the shape of tables. That's what Pandas is all about. The name itself, Pandas, is derived in fact from the term panel data, which is an econometrics term for multidimensional structured data set, which basically are table. Since we're using a new library, I always invite and suggest to look at the documentation. So you can look at the user guide or the API reference, as we did previously for NumPy. And it's nice because all the functions that you have in Pandas, you can find them here, and you can understand what these functions do. In order to get started, as always, we need to understand how to install Pandas. And a way of installing Pandas is, as we did for NumPy, pip install pandas. So we can just type this command and we install it. Obviously, when it's installed, we need to import in the session that we have it open, and we always do as this command import pandas. Now, for simplicity, we also give an alias, in this case spd. We don't have to type the old pandas, but we can just type pd to call the pandas library. So as I said, Pandas is entirely designed around data frames. More importantly, there are two main data structures in Pandas, the so-called series and as well as data frames. As we did with NumPy, we start with one-dimensional arrays. In NumPy, there were just vectors or array. In Pandas, we have series. So a series is one-dimensional labeled array that can hold any data type, integer, strings, boolean, or other kind of objects. Is a labeled structure, so that means that each element in the series has a specific label or index. When we put several series together, we build a data frame, which is a two-dimensional labeled, again, data structure with columns. And again, it supports multiple data types. So we're going to have a look at Pandas series first, and then we can look at data frame. So Pandas series are one-dimensional labeled array capable of holding any data type. It has to be an homogeneous structure. That means that all the data within the series has to be of the same type. So they are all numerical, for example, all characters, all Boolean values. It has to be homogeneous. We can have a choice of what data type we want to have, but they have to be consistent. Is a label structure. So each element in the list will have a label. By default, and this can be changed as we see in a minute. By default, the label will be the series element number. So position 0, position 1, position 2, and so on and so forth. So for example, let's create a series of numbers. So as we did before, we create first the initial list. In this case, we're using the function range. Now this range function, as you can see, doesn't have anything before. So it doesn't have pd.range or mp.range. This is because it's a Python built-in function, and it creates a range of numbers from 1 to 100 of step 5. So basically means 1, 6, 11, 16, and so forth, until so on and so forth until we reach 100, or we get over 100. In this case, the maximum number we can get without going over 100 is 96. The following number would have been 101, and since it's above 100, we're going to stop at 96. And then after we create this number series, we can transform this series into a Pandas series. And in fact, we have these pd.series numbers. As you can see, if we inspect the series here, we have the actual element of the series here, 1, 6, 11, 16, 21, and so forth. And then the label, 0, 1, 2, 3, 4, and so forth, up until we reach the limit of our series, which is position 19, as you can see here. Moreover, we have the specification of the data type in the series. And in fact, we have this integer 64. So it's telling us that our data is a series of integer elements. And in fact, we have all integer numbers here. This is a Pandas data frame. As we said before, is a structured element of data type, in this case, all integer, with a label. So these are the indices or the labels of the series, and these are the actual element of the series from 1 through 96. So we can also create a different series which contains strings. As we said, and Pandas series can contain several data type as long as they're homogeneous to each other. So we can create a few strings. In this case, this phrase here, how are you? And then we can transform these into a Pandas series. Now, these are strings. Strings are defined with double quote marks. So when we have double quotations, everything inside is treated as a unique string. And we have here In this case, we have a series, Pandas series of 5 elements, which they are all Python object. In this case, they are strings. And in fact, we have them here, and each element, as you can see, is what we defined here previously. We can also mix numeric and string data types. However, Pandas will modify them internally. So let's see what I mean. So we can create a series as well with the as always with the function pd.series. We give a list. In this case, we have some numbers and some strings. Again, numbers, and then we have strings. And then we can create the series with the command pd.series. As you see here, the compiler is not complaining. This is a perfectly valid instruction. However, we saw and we know that series needs to be homogeneous in type. The compiler, it's not complaining, it's not giving us an error because it's implicitly transforming everything into strings. So since we can transform a number into a string, but we cannot transform a string into a number, Pandas is transforming everything in the most comprehensive data type behind the scene, and that's what we have. In fact, everything is a string, and we have our elements. So this is not a number anymore, is interpreted as a string. So everything is transformed into the most comprehensive data type in the series. So we see here that we have these indices. Now these indices represents the name of the specific element. In this case, their names for now are just the position 0, 1, 2, 3, 4. However, nothing is stopping us to give proper names for more explicit and explanatory value. And this is how it's done. As always, we create a series. In this case, is a series of, more specifically, a list of 4 numbers. And then here are the indices we want to give to these 4 numbers. And these are the names that we will have as indices. We can create the series as we did before, but if you pay attention now, we'll specify the index. By default, if not specified, the index will be the position into the series, from the position of the element into the series, from 0 to n minus 1. Here instead, the indices are named, and the names are this subject that we have here. And in fact, we see the series this way. And it reminds us that they are all integers. This comes in handy because if I have to refer to a specific element of the series, for example, English, I don't have to remember there is a position 2. I can just refer it and call it with the name itself, which is English. A more concise way of define this series is with the aid of a dictionary. Now, you may not have seen dictionaries in Python before. So let's have a look what dictionaries and what they do. So a dictionary is a data structure defined with curly braces, and it's defined with 2 key value pairs. So we always have a key, so for example, key 1, and a specific value. In this case, for example, number 1. We can have as many elements in the dictionary as we want. So for example, we have key 2, and a value is, for example, 2. And we call it, for example, we can call it D as the dictionary. Now, the advantage of having a dictionary is that we can access the values of the dictionary by naming the key. So, for example, we can access value 2 by saying D and slicing what value we want. We want the value key 2. So this instruction will in fact return this value here. So it's a concise and fast way to define key value pair. When we have a dictionary, exactly as we did before, so these are the keys and these are the values. We can create a Panda series in the same way, starting from data. This, since we're passing to the function the argument data, it will infer the type automatically. It will understand that this is not a list as we did before here. This in fact was a list. And it will understand that since it's a dictionary, data, so value and indices are entirely contained in this dictionary, and therefore it knows that the indices needs to be taken from the keys of the dictionary we're passing, whereas the values or the elements of the series are to be taken from the elements of, like, the values elements of the dictionary we're giving. So it's exactly the same as we did before, but it's a more concise way of doing it with the aid of dictionaries, which are built-in data type in Python. Sometimes we can have missing values. So missing values basically means values that we do not have. Is a null value, or sometimes it's called NaN, not a number, or sometimes Na, not available. And in fact, Pandas will display here NaN. So why we have not a number value here? So how these nulls is even originated? Is originated because we passing this data here, which is this one here. However, we specifying that we want this index as subject. And if we pay attention to this list here, we see that we have art and craft that we do not have in this dictionary. And since this subject takes priority, is trying to basically match this subject to the data we have here in the dictionary. And since we don't have anything art and craft, this is specified as NaN. It's not available. It's something that is missing. Is an empty value, something that it's unknown. So these basically are the main method of creating a Panda series. So either from lists or from dictionaries. The advantage of specifying a series from a dictionary is that the indices or the labels are implicitly created, whereas when we specify a series from a list, if we don't want the default choice, we need to manually specify the name of the indices. But once we have specified the series, we can actually look how to manipulate this series. And Pandas help us achieving this subject with some built-in methods. So the first thing to notice is that this function here, or more specifically this method, it's not coming from Pandas itself. So we're not doing Pandas is null and giving the series here. We're actually calling the isNull method directly on the series because it's a method of this class, it's not a function. So what this method does is null. It's basically checking element by element if we have not available elements, if we have nulls in the series. We know that we do. In fact, we have one value here, and in fact is returning Boolean values. So this logical value, false, false, true, and false. In fact, the only value that is missing is this art and craft. And in fact, we have here art and craft as true. The opposite of this is not null. So in fact, we have the same series and different method, not null. And in fact, you can see where we had false before, we have true now. So it's exactly the opposite of what we saw before. Is the inverse method of actually checking if it's not null rather than if is a null value. We can also slice the series with logical constructors as we did before. So slicing the series, basically we use brackets, square brackets here, and we do the series that we want and the logical condition. In this case, we want mark series greater than 75. Now, these instructions in the square brackets, we are basically having a logical constructor. So this mark series greater than 75 will return as many elements as the initial series with true and false. So if it's greater than 75, basically, and this is the series, we're gonna have um, false, true, true, and false again. However, we're not interested in these Boolean values directly. We want to apply these true and false to the initial series. And that's why it's going to retain only the element of the series that have got a corresponding true value within the square brackets. And that's social sciences and science, respectively 86 and 89, as we can saw here. 89 and 86. Now, let's assume we created a series with either method and we realized that we made a mistake. So maybe rather than science 89, we want to have science 98. We had a typo, we had a mistake. We want to change this value. A fast and easy way to change a value rather than deleting the series and creating from scratch altogether is identify that specific value only and assign another value with the equal operator. So we have the series, we get that specific element through the index, and then we assign a new value. And in fact, as you can see here, we have a new value assigned. It's a fast and easy way to reassign a value rather than creating a series from scratch. We can always check individual element. So we identify the individual element and we do a logical check. So as we know now, in order to assess a specific element in the series, we slice the series with the index value, and then double equal means is equal to. So we're basically asking, is the marked series maths element equal to 73? And it's false because we know it's equal to 60. So it's not equals to 73. Another way of achieving the same purpose is rather than slicing the series in this way with maths, we can call in this exactly equivalent way with the dot. So we do mark series dot name of the specific element. These two instructions are completely equivalent, and it's just your preference to use one or the other. But we can do logical comparison. Other operations we can do with series is basically sorting and ranking them. And we're going to see what that means. So sorting basically means taking the series and rearrange them into a sorted series. Ranking instead basically means taking a series and for each element tell us the rank, which is the position which the specific element will sit if the series is sorted. And it's going to be clear in a second what that means. But let's start with sorting. So as we did before, we create a series. So we have pd.series and a list, which is the series itself. We have 23, 45. This np.none is a way to create a null. So we have a couple of nulls, one here and one here, and then all the other numbers. And this is the series that we have here. And these are the corresponding nulls value. We can decide to sort the series with the method sort value we see here. How? In an ascending fashion, so from the smallest to the biggest one. And in fact, we saw it here. Null's value will always be put at the end. Same thing if we want to do from the biggest to the smallest one, we can do ascending equals false, and it's the exact opposite. And again, null's value are exact at the end. One thing to notice is that the indices of the series do not change. So for example, what it was index 3, 41 is still index 3 and is still 41. So the indices do not change. This is achieved, this is done to avoid confusion. In fact, index 3 is still 41. As I was saying, this is done to avoid confusion. So we know that whatever element is at that specific index will always be at that specific index. Imagine what happens if indices will be reassigned. So maybe maths 60 will become another one, and science maybe is not 89 anymore, maybe becomes 86. if indices are reassigned, it can lead to confusion. And therefore, that's the reason why they stay the same. It's just the order of the series in which is shown that is changed. We can also sort a categorical series. So strings are actually sorted alphabetically, as you can imagine. So we have a series of characters, A, J, D, F, T, A. And in fact, we have them here, A, G, D, F, T, A, with the relative indices. And Pandas, Itella, these are non-numbers, are in fact characters. So we can actually sort them ascending, and in fact, they sort them alphabetically. A, D, F, J, T, with, however, the indices, the labels, still assigned to the right element as we did when the data series has been created. And then we can, in fact, sorting them ascending. So we sort them descending with the ascending argument set to false. So counter we have the opposite order. So inverse alphabetically. So we start from T and we go to A. This is how to sort them. I mentioned we can rank them, and we rank them basically. We use the rank method. We specify if we want them ascending or descending. So maths 1. So ascending means from the smallest one to the biggest one. Maths is position 1. That means it was the smallest value. And in fact, if we look at the initial series here, it was in fact the smallest value. Science is the highest value. So in this case, we'll have rank 4. And in fact, it has rank 4. And then 2 and 3. So these are the main operations we can do with Pandas series. So we saw how to create them. We saw how to do some operation, how to treat null values, how to access and slice indices, and how to rename indices as well. We're going to look now at Pandas data frames. A data frame is basically a tabular representation of data containing in an ordered collection of columns. And these columns are, in fact, Pandas series, as we saw before. Each column can be a different data type. So we can have numeric data type, strings, Boolean, or a different kind of object. However, since we know they're series, as we saw before, they need to be homogeneous to each other. The data frame, since it's a two-dimensional data structure, has got two indices, row and column. And it can be thought in a way as a dictionary of series, where they all share the same index for the rows, but different indexes for the columns, which are basically the key of that specific column. So being data frame two-dimensional, it can be used to represent higher dimensional data. It's still in a tabular format. It can have hierarchical indexing, as we can see now. So the first thing we're going to do is to create some data frames. So we're going to learn how to create them. As we saw for series, we have several ways of creating data frames. So we can start with a dictionary. Now we know what dictionary is and how to create a data frame from a dictionary. So in this context, we created a dictionary, which we call it data. We give 3 names, subject, marks, and CGPA. And then here we have a list. This list is in fact our series itself. So we have 3 lists and 3 names. As you can see with the command pd.dataframe, and we give the data as an argument, we create basically a data frame. The column index are what we specified, subject, marks, and CGPA. So we have here subject, marks, and CGPA. The row index, since nothing is specified as before, are the number from 0 to n-1. And then the body of the data frame is those lists that we have here, that we specified before. We can also create a Pandas data frame from Pandas series. So we specify 3 different series, subject, marks, and CGPA, exactly as before. If you notice, however, we have 3 individual Panda series with a NumPy with a Python list inside. We have a Panda series here and here as well. We can therefore create a data frame with the command pd.dataframe, and we give as an argument the list of these 3 series and the name of the indices, subject, marks, and CGPA. What you immediately notice is that Pandas data frame are stacking the list on top of each other. So one above the other, as you can see here. However, for what we are used to see and for our needs, we need to create vertical data frames. So we can just transpose this whole creation, this whole structure, adding .t at the end. And as you can see here, everything is transposed. So by giving the 3 Panda series in the first argument, the name of the indices, and transposing this object, we create the same exact data frame that we did before with the dictionary. Here and here. These are exactly the same. And as you can see, the indices of the columns are the names that we specify here. And the indices of the rows are, since nothing is specified, are usually the numbers from 0 through 5 that we have here. We can also create data frames from lists. So as you can see here now, subject, marks, and CGPA are lists. So they are lists containing these square brackets, 1, 2, and 3 lists. As we did exactly before, we put this list into a bigger list. So this is a list of lists and will be the body of our data frame. We specify the index, subject, marks, and CGPA. And remember, by default, when using this approach, data frames are created horizontally, but we want a vertical data frame, so we just transpose the whole object, and we have again the same data frame as we did before. So these 3 approaches, actually dictionary, list, and Panda series, these 3 approaches lead to the same data set, to the same data frame. However, we have used 3 different data types. So Panda series, dictionary, and list. Dictionary, as the same for series, is the way of doing it which is most concise. So less code and is created. We don't have to worry about specifying indices, and we don't have to worry about transposing. Everything is self-contained into the dictionary. However, we can also create this, have the same results when create data frame for series and from lists as well. Usually, when we do analysis and data science, however, we barely create data frame from scratch. Usually, data is given to us or is stored in a different format. One of the most common file type of storing data is definitely CSV. CSV stands for comma separated values. So it's basically a text, a file of text, a text file in which we have a series of data separated by a comma. Each comma basically represents a different column. And then we have, when we break the line in the text file, we represent a new line. Pandas offers a very easy built-in method of loading CSV into data frames, into the session. So we have the function pd, because we call the pandas library, dot read CSV. This is the function we're using, read CSV, and then we give the name or the path of the file that we want to import into the session. So again, pd.readCSV and the name of the file that we want to import in the session. Then we do, to check, we can do type of this data, and in fact is a data frame. We can also print it, and we see here. So taking a look at this data frame, we have 23 rows starting from 0 to 22. We have the first column defined as age, is a numerical column, more specifically integers. We have weight in kilograms as the second column, again, a numerical column, more specifically integers. And then we have height in meters. Again, a numerical column, more specifically here, we have floating point numbers. This is we are printing the old data set, which is this one that we see here, the old data frame. Again, these are the column indices, and these numbers, 0 from 22, are the row indices. We can also decide to print only the first 5 or the 5 rows or the head of the data, and we can call data.head. So we call the method head on the data frame class. And we have the first 5 observations. And again, we have age, weight, and height. So this head function takes an argument inside the parentheses. However, if not specified, its default value is 5. This argument represents the number of lines that we want to display. So here, as you can see, there's no argument, and in fact, we have 5 lines displayed from 0 through 4. If we want to do more than that, or different or less, we can just do data.head and specify the number of rows instead we are interested in displaying. In this case, it's 9. And in fact, we see that we have 9 rows displayed with indices from 0 through 8. Similarly, we can do tail, which is the last observations in the data set, without any argument in the function, is the last 5. If you're interested in more or less, we can specify a number. In this case, we specify 14, and the data is displayed here, and we see the last 14 lines of the data frame. This is a useful method to check the data. Sometimes, and very often actually, we're going to have data frames that are way more than only 22 columns, 22 rows. So it won't be possible to display the whole data once. And that's why we can investigate how the data looks with head and tail method. We can also check the shape of the data frame in order to obtain the dimension of the data. There is an attribute in the data frame, which is shape. And in fact, we do data.shape. As before, and in fact, exactly the same as we saw when we looked at NumPy package, the first number always represent the first dimension, which is rows. And then the second dimension represents columns. So this data frame, as we knew, has 23 rows and 3 columns. Is something that we knew already by looking at the data frame itself. All these data, we said that data frames can have multiple different data types as long as they're homogeneous within each other. So for example, age, they are all integers. Weight, they are all integers. And height, they are all floats. They're different to each other, but consistent within each other. This can be retrieved with a dtypes argument, which stands for data types, and it says age is an integer, weight is an integer, and height is a float, something that we knew already inspecting the data frame. A faster and easier way to retrieve all this information, so the shape, the data types, the type of the data frame, the name of the columns, would have been with the info method from the data. So this could have been achieved by doing data.info. In this case, is a faster method to retrieve all the information that are available from the data frame. So as you can see, the first thing it tells us is what is this data? Is a data frame class. It's got 23 rows ranging from 0 to 22, as we saw before. We have 3 columns. The first column is called age. It's got 23 non-null values, and they are all integer, as we saw before. Column 1 is called weight, 23 non-missing value, integer. Data column 2 is height, 23 non-integers, and there are floats. And then here we have a summary of the data types we have. One column of floating point values, and two columns of integers. And it also tells us the memory that is taking on the disk. So again, rather than finding this information one by one, shape, the types, the type, so the class, we can just do data.info in order to retrieve all the important information in one go. As I told you already, each individual column in the data frame is a Pandas series. And in fact, when we call the individual column, we have, by using type, it tells us that this specific column is a series. Now, the data is a data frame. However, the individual columns are in fact series. And you can see here age, weight, and height. An equivalent way of slicing this specific column, as you can see in these other two cells, would have been by using the square brackets and then the name of the column in quotation marks. And these two commands are exactly the same. You can just pick and choose wherever you prefer. So this is how to create a data frame and get some information about the data frame itself. The support that Pandas offers doesn't end here. In fact, in Pandas, there are a lot of tools and functions to manipulate data frame. And we're going to look at them right now. So the first thing we can do is adding new column and maybe new rows. So let's assume we want to create a new column, which is the product or a specific function on other columns in the data frame. So we create this column BMI with this syntax. We do data, which is our data frame, and then we specify a column. Since this column does not exist, Pandas will create that column for us and will assign the values to these newly created columns based on what we specify here after the equal sign. In this case, we want to take the column weight divided by the column height squared. One thing to remember is that we squared with this double star operator and not with the caret operator. So we do not use the caret operator. This means in Python XOR or exclusive OR and is not raising to a power. Double star, it does raise to a power. Anyway, having created this new column, and we can actually see when we call the data, and in fact is here, and how this is created exactly at these function or operations that we just specified here. So one column divided by the other one squared. And if we call the shape now, we can see that we have the same number of observation. However, we have an additional column. We had 3 before, now we have 4. We can also decide to add a new row. So a new row will basically add a row at the bottom of the data set. So here we create a copy of our data with just the function data.copy, and then we add a new row. Now, in order to specify the new row, we need to pay attention to two main things. First, where we want the row. So at the bottom. So here we say .lock, which is the location where we want it, index 23. So it will be here. So we add a new row after the data frame at the bottom. And then at this location of the data frame, we add this row. So now we know that our data frame now has got 4 columns. So Pandas expects a list of 4 elements consistent with what we have. So 45, 85 1.8, and 26.3. And as you can see, this is the new row we added: 45.25, 45.85, 1.8, and 26.3. So allocation 23, so basically means index 23 at the 24th row, add these observations. And as a list, it is a list of 4 elements because they need to be consistent with the columns we have in Pandas, in the Pandas data frame already. Otherwise, we'll raise an error. We can also use another indexing technique rather than using lock, and is ilock. Now, the difference is that lock means location, whereas ilock means index location. So index location, basically we give an index. So sometimes the index maybe did something different than a numeric series. And that's why sometimes we use ilock. So here the index of the rows is numeric, so we can use ilock with the numbers. And in fact, we do ilock 2. Basically, this means give me the row at index 2, which is this one here. So 54, 78, 1.5, 54, 78, 1.5, and 34.66. So index location 2. Nothing is stopping us to ask for more than one row. And in fact, we need to give a list of indices. In this case, 4, 7, and 10. And in fact, we can see here they are retrieving row 4, row 7, and row 10. So index lock or ilock, and then the argument is a list of the rows we want. We can also give a range, as we saw before. So ranges are created with this colon operator. And one thing to bear in mind is that we create from 12 to 17 minus 1. So it will be 12, 13, 14, 15, and 16. This number is not included. And in fact, we see here that it's not included. We can also specify 2 indices if we want the numbers and the columns as well. We want to subset on both dimension, and that's how it's done with ilock. So the first dimension always specifies the rows, and we have column. When we don't specify the starting and an ending point, basically means from the beginning to the very end. So we include all the observation. What column we want? Column 1. Column 1 really means the second one, which is basically the weight. It's not the age. So if you look back at the data, 60, 43, 78, and the weight is 60, 43, 78. This will be column 0, and this is in fact column 1. And since we are asking for column 1, this is exactly what is returned to us. We can also select the last column with the minus operator. So when we put a minus in front of the index of the column we want, or the rows, basically means counting from the bottom. So -1 means the last column, which in this case is the BMI indicator. We can also count from the bottom. Similarly, when we ask for rows, we count from the bottom. If we want to select the first 2 columns, as did before, we can specify a range. So this is column 0 and column 1 with this range operator. Now, in fact, we don't want all the columns. We want just the first 2, and that's why we specify the start and end point, 0 and 2, which basically means 0 and 1. We can also do a subset along the rows and the columns. So from 5 to 11 and from 0 to 2 in this way. So basically means observation 5 through 10, because it is always -1, and column 0 to 1. That's why we have these 0, 2. We can also use lock the same way. But loc, rather than taking the indices, so it doesn't take integer, it takes the name of the weight itself. We do that by specifying the name, and in fact we have weight and BMI, so the indices of the column itself. These exact same instructions could have been written with iloc as in this way. So weight was the third column. So 0, 1, 2, and 3. So it wants weight and BMI. That means column index 1 and 3. So this exact operation I was about to say can be done with, we said, 1 and 3. So basically, this is saying, give me rows from 1 through 5 and columns 1 and 3. Here with iloc, which takes the integer, the index in its argument, wherever location takes the name itself. As I said, these are two exact same operation. However, it may be more beneficial to use the name of the columns if we do not remember or we do not know the BMI is in fact in column 3. Sometimes we may have a lot of columns and it will be hard to associate a position with the name. So in order to just address the column with the name, we can just use loc to make everything easier and faster, rather than counting and understand the BMI is in fact column 3. One thing we can also do is get the whole column, just specifying the name. This is something that we saw before. So in this case, we get the age column. And similarly, we can see that we can also specify one column just with the brackets and the name of the column itself. Similarly, we can specify more than one column. So we give a list of 2 column names, the one we want, and we have them here printed to the screen. When we do not specify anything about the rows, like in this case, we want the whole series. So all the rows, basically all the observation. As you can see, we have here the full data here. We can also sort the data set. So as we saw during the series, Pandas series analysis, we can also sort the data with the same method and works in a very similar way. So here we have the data, the head of the data we want to sort. And in fact, we can give data.sort values. So Pandas data frame has got a method which is called sort values, and we give the column we want to sort against or according to. And as you can see, age 45, 12, 54, this is the data frame. And when it's sorted, in fact, age is sorted 10, 12, 21, 23, 23, 26, and so on and so forth. We can also decide to sort in a descending order. And in fact, exactly as we did with the series, we can specify ascending equals false to order the data descendingly. So from the biggest one to the smallest one. When we do not specify anything, ascending is supposed to default to equals to true. And in fact, we see this one, 10, 12, so on and so forth. As you can see, one thing to notice that the row indices do not change. They're just shuffled to avoid confusion. So wherever it was a label 19 is still a label 19. So we don't get confusing results if indices are shuffled around. We can also, as we did with series, rank the data set. So in this case, we want to create a new column, which is called BMI ranked, which is the ranking of the BMI. Remember, ranking means give me the position of that specific element if the data set would have been sorted. So we decide to rank descendingly, and we use method min. Now here we could have written false rather than 0, because false basically is interpreted as 0, and true, so we could have written true, or we could have specified 1, is interpreted as 1. And then we have this method which is called min. Now, the min method basically does the following. When two values are the same, for example, this value here, 44.39, and this value here, 44.39, assign the same rank. So in fact, position 1 and position 1. However, one thing to notice is that if we have multiple instances of the same value, in this case, in fact, we have 3, which is 1 here, as we saw, 1 here and 1 here. Rank 2 and rank 3 do not exist because their space is taken up by the repetition of rank 1. And in fact, the next one is rank 4. And that's what this min method does. So basically, assign the same rank to equal values, but then it skips position how many equals value we have. If we want all the position, we can use the method dense, which is the same thing, method equals dense. And as you can see, we have all the same, all the ranks from 1 through 23. However, sometimes we run into the issue that the same values have different ranking. So for example, this 9.8 here has got rank 1, and we have another 9.8 which still has rank 1. So we have all the ranks, but sometimes we can have multiple values, multiple ranking with the same value. An example we had before, whereas here with minimum we do not have that issue. So no rank is skipped in the dense method, basically. Another interesting feature of Pandas is to check for missing values. When we have missing values, basically we saw this in the series, we have a null or an A or a not a number, or basically a number that is not available. It's interesting to know in a fast way how many missing values we have, so we can decide what to do with those missing values. So as always, we import the data. So with the command read CSV, here is an already prepared CSV with some missing data. And as you can see here, in fact, age has a missing value here, weight has a missing value here and here, and height has a missing value here. So we can use this command, which is called isNull and then sum. Let's have a look at this command more in details and understand why it works. So the first thing to say is that missing value can actually be retrieved with the command isNull or isNA. It's exactly the same thing. So the command isNA or isNull, I can show you in a second here, gives the exact same result. But it doesn't give directly a count. It just gives us the same data frame with this check performed on each element. And in fact, we have false and true. But based on what we said before, the false and true are actually 0 and 1 behind the scene. They can actually be used into calculation. And in fact, we are summing the true value. The true value is basically answering, is this not a value? And in fact, we have 1, 2, and 1 as we saw before. As I said, we could have used the isNA and it would have been the same result. IsNA and isNull are aliases of each other, and you can use both wherever you prefer. So this is basically how to import data into Pandas as Pandas data frames and do some basic operation. Pandas, as we can saw, is very versatile, and we did just an example importing CSV. It doesn't only support CSV. We can actually import different kind of files. And here we have some methods. So we can import an Excel file with this read Excel is a function from Pandas directly. We can import an HTML file, so with read HTML, a text file with read TXT, or a JSON file directly with read JSON. Sometimes, however, we may have zip files, so we have CSV inside the zip file. And with this command, basically we are importing each CSV into Pandas contained in the zip file. So we need to use this library, zip file. You can look and download it, and you can install it as always by doing pip install zip file. So once we have the library, we can actually open the zip file. In this case, it's called data.zip, and then import the file contained into the zip file. In this case, it's called example.csv. You can also read an XML file, something that it's not natively supported into Pandas, as for example TXT or JSON. But again, with some manipulation, even if it's not natively supported, we can get it work. And how this is work? We use this XML parser. XML is a data file that is usually very common on the web. So with the XML parser, we parse the file here. And then with some manipulation, we can actually import in Pandas. And more than import, we can create a data frame based on the rows and the columns we imported through this XML file. You can download and try this example on your files. The majority of the file that are usually used in data science are definitely CSV. Sometimes you may have Excel file or a JSON file, which is a JavaScript file. So this concludes actually our lessons on Pandas. Again, a library for manipulating data frame. As always, I recommend you to look at the user guide on the official Pandas website. You can find everything you need, and anything is well described in greater details here. Now we're going to talk about visualization. Visualization is very important because it allows us to produce graphs, plots to convey our ideas, and also to see results of our analysis, also to do some quick investigation to understand our data. Two of the main libraries used for data visualization in Python are Matplotlib and Seaborn. The main library is Matplotlib. Seaborn is an additional library which uses Matplotlib as a backend. However, it's got some built-in functions that behind the scene are basically creating graphs using Matplotlib code. It allows us to create code in a faster way, and it's got some built-in function that are very nice because we do not have to write all the Matplotlib code behind it. So without further ado, let's have a look how these libraries are used. As we always do, the first thing, we need to import the required library. Do not have them installed, as always. We can install them with pip, so we can do pip install matplotlib, and also we can do pip install Seaborn. These two commands will actually install the two libraries if we do not have them available in the environment. Once they're installed, as always, we import them into our session. As you can see, in addition to the two visualization libraries, you're going to use Pandas, which is something we talked about, which is basically a library for manipulating data frames. As always, we load the dataset. So we do SNS. SNS is the alias, as you can see here, used for Seaborn. So we do SNS load dataset. Now this command sns.load dataset will load the dataset already contained in the Seaborn library. This dataset, TIPS, is a toy dataset, is an example dataset that the Seaborn library has uh, for um, for example purposes. So it's just there, built in, and is used to show the capabilities of the libraries. And this is how it looks like. So we have 7 columns, and with information of different kinds. So we have floating point numbers here, floating point numbers here, strings, and strings, which will be transformed into categorical variables, and then we have integer type here. And it's basically a table, a data set about people eating out and billing the waiters. So this will constitute the base of our um, plotting exercise. So we're going to show how to create plots with Matplotlib and Seaborn, and what we're gonna show is the content of this dataset. So let's start using Matplotlib. So as always, we can install, as I showed you, with pip install matplotlib if we don't have it. So we import matplotlib.pyplot as plt. So as you can see, the actual commands that will allows us to produce plots is very long. It's matplotlib.pyplot. So it's nice to have a smaller and quicker alias to write, and in this case, it's plt. So let's create the first graph. So we also have NumPy because we use NumPy to create some mathematical function. In this case, we do x and y. So x is a NumPy linear space from 1 through 20, and we want 100 numbers. So basically, we divide this space from 1 through 20 in 100 small intervals, and this is the numbers we're getting. And then we exponentiate each individual numbers contained in x, and then we plot it. We do plt, which is matplotlib.plot x and y. Plot is a matplotlib command that will allow us to write lines. So it's basically a line plot, and we give the coordinates x and y, and then we show the plot we just created. And as you can see, is a line plot of the exponential function that we just created here with x and y in these two lines, and then we plot it, and then we show the plot, and is basically this specific line. This the command plot from Matplotlib library has a lot of optional arguments that we did not use at this stage, and we're just using the standard default parameters. However, we can change the parameters according to our needs. And changing parameters basically means changing the type of the line, changing the color, adding legends if we want, or modifying a lot of parameters about visualization. One example is this one. So if we do not want the continuous line, but we just want points at the specific coordinate x and y, and we want stars of a red color, we just add this argument. Basically means R stands for red, and the star stands for the type of the points we want. And in fact, we want a star, so we change the shape. Other parameters, for example, are the size of the points. If we wanted these points to be bigger or smaller, we have a lot of different shapes we can choose from, or also a lot of different colors. We can also plot different lines all in the same plot, and we just give them as additional arguments to the function. So here we create the x. Obviously, if we want to create different lines, or we want to show different points in the same graph, we need to make sure they share the x-axis, because they all will be shown on the same plot. So we create the x-axis as we did before, with the first function or the first quantity we want to show, called y1, which is equal to x. So basically diagonal line. Then we do the square of the axis. So we want to show the square function, and then the square root of the axis, so the square root function. And exactly as we did before, we can plot x, and then we want to plot y1 red, which is basically a diagonal line. We want to plot again x and y2, which we do in a blue line, and then we plot x and y3 in a green color, in a green line. And here we have these lines. One thing to notice is that, if you remember, I said that y1 would have been a straight diagonal line, and in fact it is, but it's not shown in this way because the square function y2 basically makes it harder to see because of the scale. So if you, in fact, you see the y-axis goes from 0 to 400 and the x-axis goes from 0 to 20. So due to this shape, due to this scale, the shapes of the line are a little bit changed to what we would expect. We see that we also have another additional parameters, which is called title. So with plt.title, basically we add a line plot. And in fact, here in the plot, we see line plot here. It's basically, as it says, the title of the graph. As we did before, if we leave everything in a standard way to the default parameters, we do not see the title, or we do not have the title as a default. But here we wanted to add it for more explanatory value added to this plot. So we can communicate more what is actually shown here. We can also create a scatter plot. So a scatter plot basically is a collection of, we do a scatter plot when we have a collection of points and we want to show the points itself, so not when they are connected by a line. And we're going to show something from this data set we imported. So one thing to notice is that here x and y's were NumPy arrays, as you may recognize from here. However, Matplotlib also works with Pandas series. And since here we are going to show at the x and y, in the x and y plane, we're going to show the columns of this data frame. We know that the columns of a data frame are Pandas series, and Matplotlib will receive Pandas series as input and works perfectly fine as it did with NumPy arrays. So for x, we select the columns total bill, and then for y, we select the column tip. We are basically selecting this column, the first, and this column, the second column. And then, since we are interested in points now and not in lines, we do plt.scatter, and we produce a scatter plot. And obviously, we always give x and y. There are two additional parameters here that we did not use before, which is x label and y label. And again, these are very important because they add information to the plot. So the user or the reader of these plots will understand what we're plotting here. So in fact, we have total bill here and tip here. Before, we didn't have anything, so it's very hard to understand what we're actually plotting here, especially when we have multiple lines or when we did this kind of plot. The axis did not have any labels, but now thanks to this command, x label and y label, we see that we have them here, total bill and tip. These are all additional commands that will help the user to understand our graphs and make sure that the message is conveyed in the best possible way. Let's create a new one and explore new capabilities of the package. So we still want to plot x and y as x as a total bill and y as the tip amount. And we can add additional parameters to the scalar function. So we have x and y as always. Now we have this additional parameter called s, and s stands for shape. So it doesn't necessarily mean that we want all the points to have the same shape. And in fact, here we give an array of the same length of obviously of an x and y, and the same corresponding position basically indicates the shape of the corresponding points. And the shape of these points are the y's value, so the tip squared. So the first point will have a shape of y's, the first y element square. The second point will have a shape which correspond to the second y element squared, and so on and so forth. We need to make sure that the length of this array we give as a shape is the same as the length of these two arrays. And also we select a different color, green. Now we're selecting the same color for every point. We could have given an array of colors again with the same length of the points we want to plot, and we would have each point a different color. And we also give an alpha value. Alpha basically is the opacity of the points we want to plot. 0 basically fully transparent, 1 fully opaque. As always, we add the title, so it's more clear what we're trying to plot, and x and y labels, so we know what quantity are shown on the axis. And here, as always, we display the plot with plt.show. And in fact, you can immediately see that according to the y quantity, which is the tip, basically the y-axis, bigger y's have bigger points and smaller y's here have smaller points. And this is achieved through the shape argument that we did here. So greater radius corresponding to greater values of y's, and smaller radius point correspond to smaller radius of y. Now, Matplotlib, as I said, is a very comprehensive library, and you don't have to, or you're not limited just to line and scatter plots. You can do a big variety of plot, bar plot, or different kind of plots. We're gonna histograms or any other radius plot. Very many options. One thing that you want to explore is always look at the official documentation, because it's going to explain you all the capabilities of the libraries. And in fact, you have many guides, and also, as always, the reference of the functions that we're going to use. Always a good thing to read the documentation, because it can explain a lot about the package itself. So after having seen how to do line plot and scatter plot, we can actually look at bar plot. So a bar plot is used to display categorical data with bars with a specific height or length proportional to a specific value, and is the value they represent. So the comparison between different categories becomes easier, and it can be seen faster just looking at these bars. Usually in the vertical bar plot, the x-axis correspond to the categorical variable, and the y-axis correspond to the different to the value that we want to show. It's not always in this fashion. Sometimes it can be flipped, so the plot is horizontal. Matplotlib offers this capability as well. But let's have a look how to create them. So here we want to show the same data. As I said, bar plot are used to show categorical data. So we want to show smoker. So smoker is a categorical variable which has two values or two levels, no and yes. And this is how we show them. So the very first thing to do is to show how many no's and how many yes we have. So we can get the data. This is a command from Pandas. So Pandas has got some visualization capabilities, but the visualization capability from Pandas are actually Matplotlib capabilities, because Pandas in the backend uses Matplotlib to show graphs. So what we do is we get the data frame we want, we select the series. Now, as you may notice here, we are slicing the data frame with the dot and then the name of the series itself. Is exactly equivalent of what we did here. As we saw this before, these two commands are exactly the same. Then we apply the method value counts, which returns a count of data. I can actually show you what this thing alone does. So it's basically telling us the no smoker are 151 and the smokers are 93. Value counts does exactly what I said. It counts the values. There is also an additional parameter here that you can use if you want, which is called normalize. So if you do true, you have the percentages, because as you said, they're normalized. But by default, this thing is set to false. And in fact, if we don't specify anything, we have the straight count. So once we have the counts, we decide to plot them using the plot method from this class. What kind of plot we want? We want a bar plot, and we do not want any rotation. And then we show the plot. So as I told you before, we have the two categories on the x-axis and the corresponding value, in this case on the y-axis, what they represent, what they mean. Maybe we can add some rotation if we want. And as you can see, we have the labels rotated vertically. This is interesting or useful if we have very long labels. Sometimes is nice to have them rotated 45 degrees if they are very long, so it increases readability and we do not run into the issue of overlapping to each other. But for now, no and yes, there are only two categories, very small. We can leave rotation at 0. Let's create another bar plot and add some more details. So as we did before, we are still interested in smoker value. So we count the value, we plot them. We said we want a bar plot. We don't want any rotation because the labels are not that long and they're perfectly readable even in the way they are. The only thing we change is changing the color. So by default, the color is blue. Let's do green because to change and show the capabilities. Now with this function plt.text, we can actually add some text to the data, and the text is added by selecting the coordinates. So at this position, x minus 0.05 and y where we want to show them. So in this case, we want to show them as the count of the first value plus 1. So is basically the first value is no plus 1. So with one value added, and I can show you what this thing is. So this is basically y. So where you want to show that specific test, we need to give a coordinates, a numeric value. In this case, is 94. Why is 94? Because here is the count. So 151 and 93. We want to show, for example, yes, the number yes. So the number corresponding to yes, which is 93. So we select yes, which is 93. And maybe we don't want to select to show exactly a 93, but a little bit above. So we add plus 1. So we show a 94. So basically, we are showing x minus 0.005 and y 94. And what we want to show, in this case, we want to show what are we, the actual number. In this case, it would have been 93. So again, when we add a text, we specify the coordinate, x and y, and then the text itself. What do we want to show? So S is the text to be added. In this case, the number itself. And we can do the same thing with the other one. So we have the values here, 93 and 151. Here we add the title, bar plot, smoker count, and then we show the plot. As you probably recognize by now, the plots in Matplotlib are built in a sequential way. So we basically decide what we want to, how we want to create the plot and what we want to show. So first, we add the bar chart. Then we add the text. Then we add the title, and then the label, X and Y. And then at the end, we show the plot itself. So plots are built in a sequential way, adding one command after the other one. And when we are satisfied, we just show the plot. Another kind of representation is a pie plot, which is basically a circle with slices of the pie you can imagine for specific categories. Is usually used to display numerical proportion out of the 100. So we can do the same thing as we did before. Like, for example, this could have been a pie plot showing the percentage of smoker and not smoker. We're going to do something similar with the day. So the day, Sunday, Monday, Thursday, Friday, is a categorical variable again. So we may want to show the percentage of these values in a pie plot. This is what we want to show: 87, 76, 62, and 19. And more specifically, we want to show the percentage of these value, because everything will be out of 100, which is the full circle. So these are specifically the value we want to show. This is achieved with the command plot.py. Again, what we want to show, this value counts. We show the format. This is a format instruction. So basically, we want to show a percentage up to 1 decimal point. But we have the radius of the pie, so how big we want the pie, 1.2 in this case, and then the labels. And the labels are these exact labels: Saturday, Sunday, Thursday, and Friday. And we have them here. Then, as always, we show the plot. There is one thing to notice here, is that we are passing the counts itself and not the normalized count. This is not a problem because Matplotlib recognized that since this is a pie, everything has to be in percentage of 100. So it's going to basically apply this command, this parameter normalize equals true automatically. So even if we give the stray raw numbers, the compiler, the instruction will actually transform these into percentage directly. We can also do an exploded pie plot. An exploded pie plot is used when we want to draw attention on a particular slice. So the command is exactly the same. So what we want to show, the format that we want to show, how big we want the circle, the labels, and then what we want to explode, what kind of slice we want to explode. And this we just have to give a list of coordinates and how far we want the slice to be exploded. So how far from the center we want it. And that's why we have this list of numbers here that tells us how far has to be from the main circle. So this explode parameter tells us which slice we want to explode and how far we want it. Another variation of a pie plot is a donut plot, which is the same with the circle in the middle. We use the same function. So we created a pie plot exactly as we did before. This is the same command as we did before. Now, Matplotlib does not support donut plot directly. However, we can create them with the trick, which I'm going to explain now. So we create a pyplot, a standard pyplot, and the way we use to recreate this circle in the middle is basically creating a white circle and placing in the middle. And this is achieved by creating an initial plot, a standard plot. Then we create a circle. So achieved with the circle function, we give the coordinate where we want it, 0, 0, basically at the center, and the radius 0.5, how big we want it, and the color. Now we initialize the plot with GCF, the graphical device, and then we add the circle to the plot. With this command, plot graphical add, and then add artist, we can basically add different shapes we create on top of the plot. So basically, what we did here really is creating an initial pyplot exactly as we did before, and then on top of this one, we superimpose a white circle to give the impression that there is a hole in the middle. As I said, donut plot are not natively supported in Matplotlib, but can actually be created with this trick by creating two different graphs and add one on top of the other. And then we see this one. With basically we adding a white circle at the middle of, because coordinate 0, 0, at the middle with the radius of 0.5. And that's what we have here. Another kind of plot that we want to create is a histogram. Histogram is used to display the distribution of random variables, specifically and more often continuous variable. So one axis basically represents the range of the variable, which is the x-axis, and the y-axis shows the frequency of the data point. So how often that specific value is shows up in our data. We can, for example, decide to create an histogram of the tip column. And this is easily achieved with plt.hist, which stands for histogram. We just specify one coordinate because it knows that this will be the x-axis and the y-axis is the frequency by default. And then how many bins we want. We want 5 bins, and I'm going to explain in a second what this means. And then, as always, we add additional parameters, in this case, the title and the X and Y label. And as you can see, we have 5 bins, which correspond to 5 bars, 1, 2, 3, 4, and 5. It's important to look at the range. So the full range is divided into 5 bins. And what this plot is showing is that we have 120 people that gave a tip between 0 and $2.5. Then we have around 95 people which gave a tip between $2.5 and $4.5, and so on and so forth. So this is called an histogram, and it shows the distribution of a particular variables. On the x-axis, we have the values, the range of the variable we want to show, and on the y-axis we have the corresponding frequency. We could have done more or less bin if we want. In this case we did 5. We can do more if we want, and see we have more bars. In this case, in fact, we have 10. Having too many bars with not enough data may confusing results. And for this data frame, which is not too big, 5 bins is more appropriate than 10. Another one is a box plot that Matplotlib offers. So the statistics include the first quartile, the median, the third quartile, the maximum, and the outliers. It's going to be clear in a second what we mean with this quantity, but it's basically used to display, again, the distribution of a variable in a very, so is conveying almost the same message that this plot is giving, but in a different way, and sometimes is more of immediate comprehension. And let's have a look how it's done. So again, it's easily created with the box plot function, and then we give the variable we want to show. In this case, the total bill column in the data frame. So if we ignore all of these for now, we can see what the box plot is doing. So the box plot is showing the distribution of the variable. And I said the first thing that it shows is the median, which is this line here, so around $20. The median basically is the point in which we have 50% of values below the median and 50% on value above the median. It shows the first quartile, 25% percentile, the third quartile, 75% percentile, and it shows the outliers, which are here, and the outliers, sometimes they can be below here. Outliers are defined as the point they are 1.5 times the interquantile range from the median. And the interquantile range is defined as Q3 minus Q1. And this is the box plot. So the majority of the points are in fact in the box, and then we have the outliers. Sometimes this is called box and whiskers plot, because we have box here and then the whiskers here on the other side. Here, in order to make the plot more comprehensible, we adding the labels with the text function. Then now we know what it does. So we have to specify the coordinates, so where we want it. So the first one, we want to display the mean. So we display x 1.1. Since the box plot is displayed at x equals 1, we want 1.1, which is a little bit on the right, so it's not on the graph itself. And we display the minimum. So we take the Pandas series and we extract the minimum. And what text we want minimum. And is in fact here corresponding to the minimum of the graph itself. Then same thing, we do the force quantile at 25%, the median, the quantile at 75%, and then the maximum. And we have it here. And this basically this text here. These are descriptive text that add information to the box plot. So it clearly shows what this box plot is representing. And then, as always, we add the title and a label, so we know what we are actually showing. We can show some call out. This is called a call out, and is achieved. See here, we didn't have it. So if we want to draw the attention on a particular point of the graph, we can add a call out with an arrow. This is achieved with the function annotate. So I'm going to explain this in a second, but everything is the same. We just add this arrow to annotate. So how do? We create these with Matplotlib. We use this function, which is called annotate. We say, what do we want to show? We want to show outliers. And in fact, here is outliers. And we need to give the coordinate xy, where to show the arrows, and the coordinate of where to show the text. These two, because we're showing two things, the text and the arrows. And here, in fact, are the coordinate of the arrows and the coordinate of the text. And now here we say we give these additional parameters to describe the type of the arrow. So we want a black arrow, and then the style simple. So a simple arrows. Matplotlib has different style of arrows if we want something fancier or something different, but for now, a standard simple arrow will do it. And in fact, we see this here. As you can see, it's the same exact code as before. However, we added this call out with this annotate function. Exactly as we did before, the plot is built sequentially, and then at the end, we show the plot itself. So these are basically some of the main capabilities of Matplotlib. Now we can look at Seaborn, which is another visualization library, and how things are done in Seaborn, and what kind of capabilities and what kind of use case Seaborn has. Seaborn is another very common and popular Python visualization library, which is based on Matplotlib. So the backend of Seaborn is actually Matplotlib. The library, however, provides high-level interface for plotting statistical graphs. Is using Matplotlib in the backend, and therefore we can always mix and match this function from Seaborn and from Matplotlib. The functions in Seaborn allow us to plot very complex and advanced statistical plots like distribution, regression, violin plots, swarm plot, correlations, heat maps, and we're going to see more. One thing to understand is that everything that is available in Seaborn is obviously available in Matplotlib, but it often requires more code to be written, whereas Seaborns provide nicely functions that will call all the necessary commands from Matplotlib for us. And we're going to see in a second what this actually means. The first thing we need to do, as always, is to install the library, and this can be achieved with pip install Seaborn, and then we import the package. We import the package writing import and the name of the library, in this case Seaborn, and then we can give an alias, in this case SNS, so we don't have to spell out the whole Seaborn word all the time, or we can just use this alias. Now, the first plot we're going to see is actually a strip plot. A strip plot is a scatter plot, but divided for a categorical variable. And it helps us to understand the underlying distribution. So for the base of our plots, we use the tips data data frame given that we imported before, which is in the Seaborn package. And this is an example of what we have. So we have some numerical columns and some categorical columns, as we saw before. So let's have a look how a strip plot is built. And is built with the command SNS and then strip plot from Seaborn. We give the y-axis, in this case we want the tip amount, and the x-axis, which is a categorical variable and is time, which is here, and is either dinner or lunch. And then the data from everything is where everything is coming from. There are two things to notice here. The first thing is that we do not directly specify the Pandas series from where the data is coming from. So this is an equivalent command of what we saw before, where here x and y's are just characters, and here they are the actual series. The difference is that in this case, here, Seaborn is actually taking the tip column from the data, from this data. Here is taking the time column from the data. So behind the scene, this thing is actually restructured into this one, where we have the actual Panda series from the data. Here, in this way, is faster to write because we write tips data only once rather than twice. And this is the first one of the first advantage that Seaborn actually gives us. And then, as always, we display the plot with plt.show. Another thing that I want to draw your attention before actually looking at the plot is the x and y label, tip and time. If you recollect, with Matplotlib, we had to specify plt.ylabel, for example, and the label itself. But here is everything is done automatically by Seaborn, and therefore we don't have it to do ourselves. And that's what I'm saying. It provides high-level command that behind the scene calls Matplotlib. And in fact, we see here. So this plot is showing the point distribution for this categorical variable. So the distribution of tip amount divided for lunch and dinner. One thing to observe is these are categorical variable. So really, all the points should be lined up where these two are in this way. and I'm going to show you what this actually means. So this is how they should be shown if we are respecting the data 100%. However, we add some level of jitter, which is basically this noise around the graph in order to make easier visualization. And that's in fact what we do with this jitter function. So basically jitter is true by default. As you can see, either we specify or we do not specify, it will be the same. If we don't want it, however, we need to set this to false. So basically jitter is adding a little bit of random noise, not to make plots points in the plot overlapping as we saw before. It's basically an aid and a way to help visualization and to make it nicer to the user or the reader. This is not the only way of doing it, so we don't have to add jitter when they overlap. We can also put them side by side in a line fashion, and this is called a swarm plot, and that's what we see here. So everything is the same. We want to show the plot, the swarm plot as we did before for tip and time. But since it's a swarm plot, is not a strip plot anymore, we do not add jitter, but we just put the points when they overlap, we just put them one alongside the other one in this way. And again, it helps us with data visualization because it gives a more accurate representation rather than when they are all in a straight line. So this one basically is helping us visualizing two different variables, time and tip, alongside the same the same plot in two different x coordinates, lunch and dinner. Nothing is really stopping us to add more variables to this plot, maybe by setting two different parameters. We saw an example before when we set the shape of the points, so the size of the points according to another variable, and we can do the same here. So for example, we can set the HUE, which is basically the visualization, adding the visualization of the color according to the day. So we know that the day has got 4 levels, so each point is colored based on the corresponding day. And we have here the color Thursday, Friday, Saturday, and Sunday. So we add another variable and we are displaying these variables in terms of the color. A thing to notice is that we have the legend created automatically by Seaborn. When we did the same with Matplotlib, we did not have the legend. We have the possibility of adding a legend with Matplotlib, but requires more code to be written. Whereas in Seaborn, everything is done automatically and taken care by the Seaborn command itself. So as I said, this command is calling several Matplotlib commands behind the scene, so we don't have to do ourselves. We can also talk about violin plots. So a violin plot is basically very similar to this plot, but rather than showing the points itself, it shows the distribution. It features a kernel density estimation of the underlying distribution. A kernel density estimation is basically a line that shows the underlying distribution of the plot. So it shows the distribution of numerical variables across categories for one or more categories. In this case, we have two. We can have more, and so this distribution can be compared. So here is the data. So the usual data. We want to create a violin plot for total bill amount, splitted by the day. The day we know has got 4 categories, so we expect 4 plots. And this is what we see here. So this is the distribution of the plot and is symmetrical around the axis. As you can see, we just give the name of the series and where the data is coming from. Everything is done by Seaborn itself. We don't have to specify any color. We don't have to specify anything. We have the bill label here and the day label here without specifying anything. In Matplotlib, pure Matplotlib, we would have specified ourselves. But since this is done by Seaborn, everything is done automatically. If we want a bigger size, we can actually set it. So we do plt.figure and we select a figure size. So this is the vertical and this is the, as always, the horizontal size of the plot. And then we can add the violin plot. As we did before, in this context, we can add a third variable to display an additional information. In this case, the additional information, we display the day based on the color of the plot. And here we do the same with these hue parameters. So we want to display the sex column in the data. And then, in fact, we have each different distribution. So it's not fully symmetric anymore, but it's divided by these additional parameters that we're giving. Again, legend is created automatically. The labels are created automatically, and everything is taken care of by Seaborn. Moreover, even the series are not specified. We just specify the name, X, Y, and hue, and we just give where the data is coming from, and everything is taken care automatically. And this is called, again, violin plot. A perplot is a pairwise distribution of variable in the data set. So we have a matrix, and each cell in the matrix shows the distribution of the variable. It's going to be clear in a second when we look at what we want to show. And this is what we have here. So it's a type of plot that is only done for numerical variable. And in this case will be total bill, tip, and size. So we want something a little bit bigger. So we specify the parameters of the size of the plot we want. We specify per plot and the data, and everything is taken care automatically by Seaborn. So let's discuss this plot. So we have the same variable, total bill, tip, and size here, and total bill, tip, and size here. On the diagonal, we have the histogram of the variable itself. And whereas on the other cells, we have the scatter plot between the two variables. So tip and total bill is here, size and total bill is here, and so on and so forth. Since the plot is symmetric along the diagonal, on the opposite cells, you just have the same graphs, just transposed. For example, this graph here is the same as this one, but they are transposed. Similarly, these two, and similarly, these two here. So this is called a perplot, which is useful to show the relationship between two variables. For example, we know that total bill and tip as a direct linear relationship, increasing linear relationship, and it's easier to draw this conclusion and faster looking at the graph everything at once rather than doing one by one. We could have done this with Matplotlib, but we had to build this one by one and then paste them together in the same plot, whereas Seaborn with one command is done automatically. Again, Seaborn is just wrapping commands of Matplotlib for us to make our life easier, and that's what we have here. So talking about other distribution and other visualization of distribution, Seaborn can provide a lot of commands around that. So let's have a look at distribution. Distribution is basically how the specific variable that we want to look at is statistically distributed. So we're looking at the probability distribution. And again, Seaborn is easy. This plot, and it is a distribution plot of the data we want to show. This is a very similar command to what we did before. If you remember, we did plt.hist. And in fact, as you can see, is the same, basically the same graph. The additional advantage of using Seaborn is that we also have the estimation of the density plot. So this specific line that we did not have with using Matplotlib. We can add it separately, but with Seaborn is automatically added for us. And this is the distribution plot. So it shows us the range of the total bill. It shows us the most popular ranges, and basically also shows us the distribution. So it's almost normal distributed, and we can gain this information from this line here. One thing we can do is shows different distribution for the same quantity total bill by divided by an additional variable. And let's have a look how this is done. So first of all, we need to decide what is the additional variable. In this case, is a categorical variable, and is basically, we know that is divided by lunch and dinner. So what do? Basically, we create a for loop, and we create a different subset of data, like a filter data, basically slicing the pandas data frame according to this variable. So the first run will be lunch, and the second run will be dinner. So in the first run, when we have lunch, we create exactly the same thing we did before. So this is the data, and we want the total bill. We don't want the histogram in this case. We just want the kernel density estimator, which is this line, and then we have some additional parameter, which is basically the shade of the graph here, and then we add the label, which is lunch and dinner. So the first run, the plot will create for lunch variable, and the second run will create dinner. So we're basically adding two different distributions, one on top of the other, with the for loop for lunch and dinner. So we can draw conclusion on the data. So we can see that the distribution plot for lunch is a little bit more right skewed than for dinner. And this implies that they're spending more on dinner rather than during lunch. Again, the same thing could have been achieved on Matplotlib, but would have required more and more code, whereas with Seaborn is done automatically. Another plot the Seaborn offers is the count plot. So the count plot is basically showing the count of the observation in another for the different variable. We did this before. It's basically very similar to a bar plot that we did before. With Matplotlib, we had to do plot.bar and add a bunch of arguments plus anything extra that we want to see, like for example the X label and the Y label, whereas here is done automatically. We just say where the data is coming from and what we want to show. On the X-axis, we want to show the day, and the color is given by the time, and that's we have several series. Here we see that on Thursday there are way more people on lunch than dinner. Friday is almost the same but more dinner, whereas Saturday and Sunday probably the place is closed and lunch, and we only have dinner customers. This is basically a bar plot or a count plot. It's basically a bar plot showing the count. Another useful representation is the heat map. So heat map is a two-dimensional graphical representation where we show a matrix, and each cell has a shade of the color which represents the intensity in that specific cell. A very useful example of showing heat map is correlation. So that means that as the shade in that specific cell is darker, the higher the correlation. So let's have a look how to create this one with Seaborn. So this again, the data from where we're starting from. Remember that correlation is only calculated between numerical variable, and it can be done automatically. So the data frame, which is a pandas data frame, tips data, has a built-in pandas method which is called core. So when we do correlation matrix and we call correlation, basically is calculating these matrices. So this matrix basically is only referring to numerical columns, total bill, tip, and size. As you can see, total bill, tip, and size on both columns and rows. And then we have the level of correlation. Obviously, each variable is perfectly correlated with itself, and you have one on the diagonal. And then on the off-diagonal cells, you have the correlation between the variables. And obviously, if total bill is correlated with tip, tip is obviously correlated with total bill. And that's why the matrix is perfectly symmetrical around the diagonal. Once we give this matrix to Seaborn with the heat map function, is gonna do everything automatically. We don't have to worry about anything. And this is the heat map itself. So we gave heat map, what we want to show, in this case, the correlation matrix, and we give this annotate variable equals to true. With this annotate equals true, basically means that it's gonna write in the graph the number that we want to see. So for example, this is rounded, so 68, and we have it here, 1, and we have it here, 49, and we have it here. If you remember with Matplotlib, if we want to display text, we have to do plt.text and a bunch of different arguments. With Seaborn, everything is done automatically because that function, plt.text, is called automatically from this function directly. And this is the heat map. Looking at the heat map, we can see that there is a moderate correlation between total bill and tip, 68. And then here we have the scale. So as the color tends more towards this yellowish color is higher, whereas when it goes to this bluish, blackish color is lower. This is a heat map. It's basically a two-dimensional representation where in a matrix fashion, whereas each individual cell is colored with according to the intensity or the value in that specific cell. So again, this concludes our discussion about visualization library. Two of, as I said, the most powerful and popular are Matplotlib and Seaborn, and they are very suitable for almost any visualization need that you will encounter.
If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoyed this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions, and I will respond to your comments.